Hello mathematicians, we're going to try to put some of our ideas from earlier on together now to start to use graphs to solve equations and inequations. And it requires that you think back to something that you would have learned in year 9 or 10, where if you think about solving two equations simultaneously, what you're really doing is finding the pair of values which satisfy both equations. And therefore, you're in fact finding the points of intersection of the graphs representing the two equations. So in our work with solving equations simultaneously by elimination or substitution, the equations could be drawn up carefully and the points of intersection of the two graphs read off, and that would be the solution of our simultaneous equations. So that's called graphical solution of equations. So the process is pretty straightforward. To solve an equation graphically, we sketch the graphs of y equals the left-hand side and y equals the right-hand side on the same set of axes. And then we read off the x-coordinates of any points of intersection. What we might note is that sometimes the original equation might need to be rearranged in order to make the graphs that we're drawing a little bit easier. There's another plus about solving graphically, and that is that we can see how many solutions we expect to get at a glance. So we're going to have a look at an example of this, just to point out the importance of this statement here. The original equations may need to be rearranged. So the diagrams are here below, but I'm going to just jump to GeoGebra so we get a bigger version of it. So suppose we had this equation to solve. X squared plus 1 on x equals 9. Then, according to the method above, if we draw the graph y equals x squared plus 1 on x and the graph y equals 9, then where they intersect is the solution. Now, that's what that looks like. So the blue graph is the graph of x squared plus 1 on x, and the black line is, of course, y equals 9. They intersect at 3 points, so that x value is, I don't know, minus 3, a little bit more than 0, and something that looks like close to plus 3. Now, drawing that graph in blue is a task in itself. So we need to be alert to the fact that we might be able to rearrange this. So if I just eliminate that and look at the easier form of the solution. Now, where do these two graphs come from? Well, they come from taking our x squared, sliding it over to the other side, and ending up solving the equation 1 on x equals 9 minus x squared. And 9 minus x squared, of course, is this parabola, concave down, cutting at 9, and 1 on x is our hyperbola. So we can see again that there are 3 solutions. This one here, which, as we said, is around about -3. This one here, a little bit more than 0. And this one here, which is, by the look of it, +3. So we would have the solution much more easily from these graphs than from the one up above. To actually find these points of intersection, however, we can't avoid the fact that we will have to solve this simultaneously. To solve this. And to solve it, we're going to end up with a cubic. We'd have to multiply through by x, and as of yet, we haven't got a technique for solving cubics. So the best we can do here is to say, well, there are 3 solutions and they are about that size. Now, this method can also be extended to solve inequalities. Again, by sketching the graph of the left-hand side and the right-hand side on one pair of axes, before examining which curve lies above the other at each value of x. So, for example, this inequality here, which again I'll jump back to GeoGebra to get a bigger version of. So just to let you see this graph before we bounce back again, because I can't draw on this. If we have these two graphs, the graph of the left-hand side is the hyperbola, 6 on x, so our 2 branches of the hyperbola. Graph of the right-hand side is a straight line with a gradient of 1 cutting through the axis at -5, as you can see. And we can see we expect to get 2 solutions. Now, that sort of makes sense because we know we could also do this algebraically. If I multiplied both sides of the inequality by x squared to remove the bottom line, I would end up with something which was, well, it was actually going to be a cubic, but which I might be able to solve algebraically. But with the graph, I can find the points of intersection nice and easily. So back here with my smaller version of the diagram, I can see that what I wanted was where the hyperbola is above the straight line. So the hyperbola is higher than the straight line for this part of the curve and for this part of the curve. So that means that it's our solution to this inequality. Our inequality means that once I know these values of x, which look like they'll be x equals 4 and x equals minus 1, once I know those, then it happens where x is less than or equal to minus 1, and for 0, because that's our asymptote, 0 less than x less than or equal to 4. Now, it's also really good for absolute value equations as well. So if we had this absolute value equation to solve, that 2x minus 5, mod of 2x minus 5 equaled x plus 2, our option is to draw the mod of 2x minus 5. So that is our V shape shifted to the right by 5 on 2, 2.5. You might be able to just see that there. Wish I hadn't put this hyperlink in. And x plus 2 running up there. So we could read those 2 solutions off the graph if it was drawn carefully. At the very least, we know that we would be expecting 2 solutions, and we might have to go through and solve algebraically after that, where and it would be quite involved, if 2x minus 5 is positive, so it's greater than or equal to 0, then what we get would be that 2x minus 5 equals x plus 2, and we try and solve that. And if 2x minus 5 is negative, so it's that, then minus 2x minus 5 would equal x plus 2. And away we go with that. It's also good for inequalities involving absolute value equations. And those inequalities can be really difficult to solve algebraically, but at least this can give us the heads up about sort of how many parts we expect to our solution. So mod of x minus 1 is our green curve here. Mod of x minus 4 is our red curve. Where is the green curve underneath the red curve? Well, it's underneath the red curve, or lower than the red curve for all of that part. And therefore our solution is, once we find that point of intersection just there, which by the look of it is 2.5, then the green curve is under the red curve for all the values of x which are less than 2.5. Okay, which is a lot easier than doing it algebraically, where we will have to consider cases. So have a go at these. I hope I've selected reasonably. Number 19 is difficult, obviously, but a little bit of a challenge for you.